All right, welcome everyone again, also online now. So I'm going to be talking about results from gamma ray observatories that are particle detection arrays. And what you see here is a map of the world with different observatories that I'm going to be touching upon in this presentation. So you see here the Milagro Observatory that was operated in 2000 to 2008. Then the follow-up is HAWC that started really science operation in 2015, but started taking data with the partial array already in 2013. Then we have the Tibet air shower array. We have ARGO also operated. This has been operated for a long time, as you can see. And then the LHAASO, the newest addition to this group of particle detection arrays for gamma ray astronomy. So what makes them special? It worked earlier. Don't know. Might doesn't work anymore. Okay. Should I just use this? Oh, now it works. Weird. Okay. I don't have to talk about this much. Most of you have seen this. Maybe the thing that I should point out is, again, you see these kind of three groups on this one slide of gamma ray observatories. So you see, of course, from space, like Fermi or other space-based telescopes. Then we have of course, imaging air Cherenkov telescopes, imaging atmospheric Cherenkov telescope arrays that you will be hearing about in the next talk. And I will be focusing here about particle detection arrays, which highlights here the water Cherenkov detectors that were mentioned earlier, because they seem to be kind of a really successful way of detecting particles on the ground. But of course, there are also other detectors, such as detectors that use particle detection arrays that use scintillation counters or RPCs, which have also produced very important scientific results. The point here is, I guess, of this slide, we need to go to high altitude to be as close as possible to the maximum, the air shower maximum, because we only take a snapshot of the shower as it strikes Earth. What are the main features of these particle detection arrays? I always summarize them in three. So they have all a high duty cycle, typically when everything goes well, much more actually than 95%, sometimes 98%, 99%. So this really makes them well suited for transient detection. Then we have a wide field of view, which makes them really well suited to detect extended and large structure emission. And then also, and makes it really useful for searches of any kind. And then the other thing is these particle detection arrays have a very good sensitivity above 10 TeV. And here you see some examples, again, these three groups. So what does it mean? Wide field of view plus high duty cycle. Most of you probably have seen this picture. So you have this instantaneous field of view, in this case for the HAWC detector, but that's true for any other particle detection array. And as the Earth spins, we just sweep the sky, the overhead sky, and collect data that way, integrate, and so then you get a map like that. And depending on where your particle detection array is, you get a whole in terms of sensitivity in the south or in the north. So another thing that I wanted to point out is the sensitivity of the detector, these particle detection arrays versus energy. And this is actually, I show this not only because I full disclosure, I'm from HAWC. They all look very similar, these sensitivity curves, but this is indeed a measured sensitivity curve, measured with a measurement of the Crab Nebula. So you see here the 507-day sensitivity of the HAWC detector, and then in comparison with IACTs, and you see the cross is just below 10 TeV, and then if you collect more data and you project to 5 years, then you can even go lower. So it's a really nice sensitivity to sweep across the sky. The other thing is, actually, this is kind of conservative, and some of you may have seen talks already. HAWC has new sky maps, and these sky maps are actually a lot more sensitive, especially also at lower energy than the previous measurements, due to improved gamma hadron separation and improved angular resolution. So these three capabilities allow us to do several things. So for the survey capability and high duty cycle, HAWC is particularly, or not HAWC, all PDAs, excuse me, is particularly well suited for source searches and discoveries, and there have been those catalogs and transients and alerts. Then for the extended and large-scale emission sensitivity, in particular, it has turned out that it was very useful to find new sources or a new source type that I will not be talking about very much. Northern Fermi bubble is another thing that has been measured with a PDA. Molecular cloud emission, upper limits have been placed, and diffuse emission as well. And then high energy gamma ray sensitivity, of course, is one of the things that everyone is now talking about with the latest Nature paper from LHAASO. And these are kind of the summaries. So and I'm not going to talk much about it due to lack of time, so I had to make really hard cuts in terms of all the interesting results that PDAs have presented or published in the last 5 to 10 years. But obviously, Macarians can be measured, and energy spectra can be measured for the Macarians. So you see a light curve here from HAWC. You see measurement for Macarian 501, a long-term observation from ARGO. And then, of course, alerts as in that are important in communication in multi-wavelength astronomy. Another thing is, and I'm not going to talk about this, TeV halos were not really a thing before. They have become a thing after HAWC detected TeV gamma rays, very extended emission from the region of Geminga and another pulsar in the area, the monogem pulsar. There is still debate going on what these which diffusion model or how the diffusion actually works. There are, to the left here, a model where the TeV halo is kind of in between the classical X-ray pulsar wind and the supernova remnant, or you can imagine that the electrons escaped and the supernova remnant has already dissipated. No matter what, there is a separate entity, and we keep hearing about it. We still need to study it. We need to understand it. Then, as I mentioned earlier, Fermi bubbles, molecular clouds, upper limits. I think due to the limit of time, I cannot talk about it much. But of course, please approach me if you have questions about those measurements. Now, I wanted to make a point about how much more sensitive the surveys have become with these PDAs. Milagro collected data between 2000 and 2007 to detect just 8 sources at a significance of just above 4.5 sigma. The Crab Nebula in that data set was detected with 15 sigma. Then ARGO in 2013 published a data set where they found 10 sources above 0.3 TeV, also above 4.5 sigma. And in that data set, the Crab Nebula had about 21 sigma. So improvement, that's what we want to see. Now, the latest HAWC catalog that has been published found 65 sources above 5 sigma, and the Crab Nebula significance is 190 sigma. So major improvement, and indeed that's what we want to see. So another thing that's interesting that I wanted to point out is a paper that HAAS and HAWC published together. What was done here is that HAAS modified their analysis and changed the background estimation method in order to kind of emulate the worse angular resolution of HAWC, but the better sensitivity to large extended sources. And as they did this, what was found in HAAS data is that out of 7 sources that previously had not been detected by HAAS, now 4 sources have been detected. So what this tells us, of course, is there is a complementarity here that really makes it interesting to combine the data sets between IACTs and PDAs. And it also gets better. So all of the things that I'd shown you before is the PAS4 data from HAWC and other instruments, but particularly from HAWC there was PAS4 data. And these panels show you how much our angular resolution has improved from PAS4 to PAS5, in particular due to corrections that we applied and that we understand better now about the angular resolution in our data set. And so you see that there's a lot more structure there that can be used in order to actually then come up with a source catalog, and the source catalog will then also be employing multi-source fitting procedures, just like Fermi. The sensitivity is now there. And also the other thing is we are now not only stopping at 45 degrees zenith angle, but also go to 60 degrees. Then, of course, already mentioned, the big discovery published in Nature by LHAASO of at least 12 sources that are very strong Pevatron candidates. Following that, HAWC looked at their new data set and also found 19 sources in, of course, a lot more data. I think it's really amazing to see that in 6 months of data, LHAASO found 12 Pevatron candidates. And of course, this is all based on the KM2A. Then there was an interesting publication, and you see these publications are all in about the same time frame. This is also from 21. Is a Tibet paper where they discovered, where they measured sub-PeV diffuse emission. And you can see that here for 3 different energy ranges. The point here is in particular that they measure gamma rays approximately above 400 TeV. And what they did is they, I don't remember exactly how they, what they assumed 0.5 degrees or so. They required that these are very good gamma ray candidates, but also very far or significantly away from known TeV sources. And that's what they then get. That's the fluxes they get. And they detected significant diffuse PeV gamma rays this way. Again, another sign for the fact that there must be Pevatrons in the galactic plane. Then, of course, another great measurement from LHAASO that was recently published in Science that confirmed or discovered, depending on how you look at it, the Crab Nebula as a Pevatron. What is amazing here also is that they do measure the Crab spectrum above 3 decades of energy. And what they also found is, although, you know, the devil is sometimes in the detail, but a pretty good agreement with all the measurements that have previously been published. But of course, none of these has this energy reach that have previously been published. They also, if you look into the paper, they have a good agreement between their water Cherenkov detector array in the center and the KM2A outer array. So that's very great. The thing that they found is that it's very hard to explain this, obviously. The thing that they also found, though, is that if they, I think I have another slide here, if they then use a lepton-only model, that the lepton-only model kind of overshoots here between 50 or 60 TeV to 500 TeV, but then they also have a little bit of an excess just at the PeV range here. And so the question is, can this be explained with a 1 or a 2 zone model or a 1 and 2 population model? I think the verdict there is still out, and people have been looking at it in order to understand how is this possible. The amazing thing here is the acceleration efficiency that they, through their model, get is 15%, which is 1,000 times higher than the SNR shockwave acceleration. Another thing that they found was a 1.4 PeV photon from the direction of the Cygnus region. And the Cygnus region is interesting, right, because of the Cygnus OB2 star forming region. Indeed, HAWC also measured this and made sky maps, and then used a multi-source fitting approach in order to distinguish, because right on top of this region of the Cygnus OB2 star forming region, there is a pulsar wind nebula which you need to separate out the flux from the region that could be from the component that could be associated with the star forming region. And indeed, the modeling that HAWC then applied claimed that indeed the cosmic rays could have been accelerated up to 1 PeV. So the other thing that actually then, if you look at this, is that again, multi-source fitting is important. You see here an overlay of the other measurements in that region, and they look like they are much lower, but again, it's because IACTs and other instruments measure the flux from the pulsar wind nebula and not the flux from the OB2 star forming region. It seems like LHAASO actually is indeed measuring the flux from the OB2 star forming region, because they quote a flux for 0.3 degrees in their Nature paper, and when you then extend this to the actual size of the Cygnus OB2 associated gamma ray emission, then it actually is in very, very good agreement, surprisingly maybe a good agreement with the HAWC measurement. Another thing, the Boomerang region, I think what is the time? 10 minutes, okay. The Boomerang region is another interesting region. HAWC had previously published a result of a spectrum, and that spectrum, number one, the detection is in good agreement with the Veritas detection in that region. Number two, the emission could be explained with parent particles up to 100 to almost 1 PeV, so 800 greater, at least 800 PeV. Now, since then, both Tibet and LHAASO, again in their Nature paper, have also detected 100 TeV emission above 100 TeV, and in the case of LHAASO, in fact, almost 600 TeV. So all these things are really interesting. However, what is missing a little bit is, at least at the highest energies, deeper morphology studies, because there are these two complexes who could actually produce the emission, and that has been resolved by the MAGIC IACT. They resolve a head and a tail region, the head region containing inverse Compton, or potentially the emission could be due to inverse Compton scattering from the pulsar wind nebula, or then you have the tail region, which is near a molecular cloud. And with this new data set, HAWC was able to resolve these two We just call them rather pedestrian upper source and lower source, but the tendency is the same. And currently there are analyses ongoing with HAWC, where we try to combine the two spectra measured by MAGIC and HAWC. Another thing, this is first. So another thing that I found this science paper a while ago talking about back in the day, 93 I think it was, about cosmic ray measurements via the detour of measuring gamma rays. And one of the things that people were at the time really excited about were X-ray binaries, but then they had become a disappointment because they didn't get the emission that they had hoped to see from these. Now, since then, though, things have changed, and there is now a detection of LS50 LS5039 above 20 TeV, and also HAWC has now resolved the two phases and measured the spectral the spectrum for those two. And the agreement actually is acceptable, I would call it. I think there's still some more study needed with HAAS, but the main point here is we think that the emission extends up to above 100 TeV. We are doing studies as in like, at what significance do we detect photons above 100 TeV, and our energy range goes past that doing those studies. So again here, by the way, number one, the improved angular resolution. Number two, you need to do multi-source fitting in order to kind of tease out this emission. And then there is, of course, the Nature paper from, I think, 2018, where HAWC detected emission from the two lobes of SS433, also above 20 TeV, which then made it possible to explain why ASCTs may have not seen it, because their upper limits were placed at lower energies. And we see really with these objects, we see that the emission is at very high, very high energies, I think is the right way to put it. So has now, I heard at Barcelona, has presented confirmation of this measurement. And then the latest in this group of X-ray binaries is V4641 Sagittarius. And again, we see an emission of almost 10 TeV. This is a very isolated source, so no multi-source fitting or anything necessary. But again, if you look actually at the maps versus energy, you will see that most of the emission comes in above 20 TeV. And then finally, a few words about the Galactic Center. HAWC is now also seeing emission at the Galactic Center. This in itself is maybe not so exciting, because this has been seen by other experiments before. Potentially, however, since this is a very high zenith source for us, it could be relatively high in energy. So again, studies ongoing, because the response files are not really made out to really function well at these high zenith angles. And for me also, it will be interesting to see, LHAASO is a little bit further north, but they also have a much, much better sensitivity. So it would be interesting to see what they see, and if they can see anything if they, optimize their analysis for these high zenith angles. Okay, 5 minutes left. So we can also do fundamental physics with particle detection arrays. This is kind of a summary for LIV measurements with LHAASO and HAWC. But let me talk just a few more minutes about the future. And what you see here is the response of the National Academy of Sciences to the submission of a white paper about SWGO. And I'm not going to talk much about SWGO here. There will be a talk on Wednesday by Harm, and he will tell you all the details. the point here is that I'm making is though that the panel on particle astrophysics and gravitation recommended US funding at the level of $20 million, which is what we ask for. Maybe we can get more, who knows? But it's in the timeline here for the multi-messenger program they are recommending. So for a collaboration that was formed in 2019, really, that's pretty nice. Again, maybe in the interest of time, I don't want to go into too much detail. We have a collaboration now. WGSO, which was a project, is now a collaboration as WGO, the Southern Wide Field Gamma Ray Observatory. And don't worry, this name will go away. There will be a nicer name at some point, but you know, that's how that is with, for example, GLASS and Fermi. There are 4 countries in the running for this, Bolivia, Chile, Argentina, and Peru. And I just want to say, this year is actually a big year in the sense that we are all going to visit the sites. Not all, there would be too many. A team is going to visit the sites and will look which of the sites, there are 8 sites, are the best to or preferred to be for the SWGO construction. Yes, I think, again, Harm will be talking about it. You kind of see, again, the same tendency, by the way, with these. If you look at the projected sensitivity curves, it looks like the intersection is, again, kind of interestingly at the same place, only that all the instruments became more sensitive. This is just kind of a final comment. Multi-instrument and multi-messenger analysis will provide unprecedented science output, and gamma ray astronomy will, with particle detection array, will really make major contributions. And I hope you have seen this, that actually it already has happened. And I originally started out with Milagro, and things are very different now with HAWC. I can tell you that. And then the very high energy open data format was mentioned before. I just wanted to leave you again with this this science report that I mentioned earlier, and just leave you with this beginning, the introduction to this. And I think cosmic rays are now in vogue, still continue to be. Thank you.
There is one urgent question. One question there.
Thank you for your thank you very much for your presentation. And I'm really interested in the reconstruction method of HAWC to extend the sky to 60 degrees. How can you improve the angular resolution in such a high zenith angle range?
I'm not sure what you mean. I mean, we do corrections, and we look at, like, at the very high, in fact, it's very difficult to confirm the angular resolution and the pointing. This is something we are struggling with. I've been thinking about, for example, the Galactic Center. What one could do is one could look at the HAAS measurement and then compare the HAAS location for the Galactic Center with what we are measuring, and then see if that agrees. In fact, this is how we found a small problem in our pointing in previous catalogs, when we compared the pointing of our sources with the pointing of HAAS sources and
yes, but what I mean is the more general topic, the reconstruction method of the incoming direction of events in very high, very large zenith angle range. Is it generally in the zenith angle range such as 60 degrees, then the reconstruction will be very poor, and direction generally cannot be reconstructed well. So is there any new reconstruction method of HAWC to reconstruct events with high zenith angle range?
Yeah, maybe we
Excellent.
can take this offline.
Yes, yes, yes.
I'm not sure I understand, but let's